Hello, I'm Mr. McBrien. This is TEJ3M, How to Eat a Whale. The Ontario curriculum states that we should use a design process to write, test, and debug a computer program that controls and/or responds to the inputs from an external device. Today we're going to talk about some general engineering principles that should help us to more effectively accomplish this task. So the riddle we started with, how do you eat a whale? Some would argue that the answer is one bite at a time. Today we're going to talk about how to transfer this metaphor to an engineering context. So we're going to attack this problem maybe a little bit backwards. We're going to talk about what happens when we first produce a new invention. And no great shock, we can remember from our troubleshooting days around the computers that the more complicated the device, the more things are possible to go wrong. So if our device has two aspects to it, two things that it does, it might be thinking and outputting. We'll represent those with A and B. If our device doesn't do what we expect, how do we know which operation isn't working? And the answer is, it's hard to know quite often, but we can tell that if B caused the problem and we spend all of our time trying to work on A, we could, in fact, spend hours or days or weeks on something that already works and potentially even break it when in fact it was B that was causing the problem and not A. And it gets worse. There aren't many devices we can imagine that have only two aspects to them. If we have three things that something does, for example, detection, thinking, and output, then we have three potential things that can fail. And for our device not to work, it could be A, B, C, or in fact any combination of those that could be causing our invention not to work. And what's the upshot of this? It's actually kind of depressing. Failure is exponential. So for any given function, for every function in our invention, each one of them has the possibility of working or not working. And for n functions, we can recall from our binary number ideas that we have 2 to the exponent of n possible states. So what does that mean? Well, unfortunately, the only one that represents a perfectly working device is every component working. And all the other possible states that we have represent a not working device. If we try to view and troubleshoot everything all at once, we have to consider all of those states as we work. And we can spend a great deal of time troubleshooting something that has multiple things wrong with it at once. But we see additional problems with trying to develop a device all at once. It can be extremely challenging to work efficiently on even moderate-sized projects. Each function depends on another one, and if we're trying to develop them all at the same time, it can be extremely, extremely challenging. So what we want to do is try to have teams focusing on individual components, even if it's the same team for each one of those, working at a different time of the day. And what we have to do, and we'll see how to do this in a few seconds, we need to have stand-ins for key components that aren't ready, that are under development. So how do we do this effectively? So we want to take and subdivide projects because large problems can be just too much of a problem. We want to break them into small tasks that can be executed as their own mini project. And we want to develop it on its own time scale, with its own deliverables, and then assemble the components at the end of the development process. So how do we do it? This takes a bit of practice, but I'd encourage you to think about the idea of actions. So what does a given component do? Does it accept inputs? Does it make decisions? Or does it create outputs? And those are the big things that given components do. We can break up those activities and develop them independently pretty easily. So I'll take each of those three basic ideas individually. If we're developing an input system, for example, a sensor, we can have an LED that stands in for communication to the processor. So instead of trying to develop our sensor to talk directly to our decision-making system, we can temporarily wire up an LED that will light up when the sensor fires, or a series of LEDs as necessary. If we're building a decision-making system, then we may not have an input device yet or an output device yet. So we can hard code in a user-defined value, or we can have a switch that takes the place of the detector. And we can have an LED that takes the place of the output device. And by the same token, our output device may actually just simply have a switch or a jumper initially that takes the place of the detection and decision-making system. And if we take this idea and run with it, we can develop our individual components independently of each other and then assemble them at the end. Okay. And the key to success there is to treat these components as their own project. So we might have the exact same team, but different responsibilities, or the same team and the same responsibilities. This really depends on the size of the project. We can have defined timelines, defined inputs and outputs that are not the same as the inputs and outputs for the eventual project. And it's important that we understand what our success criteria are right from the beginning. What are we hoping to achieve with this project? I won't go into too much detail on this, but it may help to think in terms of a very big project, something really quite challenging to build. Let's say we decided we want to build a tennis robot to help train professional tennis players. We can start with our requirements for the overall invention and then start to substitute. And I'll do this for us. If you want, you can pause the movie right now and think about this yourself, about what the various stages of a tennis robot would be. So when I went through this quickly, I thought in terms of we would need sensors to track a ball in terms of speed and distance. We would have to be able to predict its path, move into that path, decide what we want to do with the ball, and then hit it. And then, of course, move into a waiting position to see whether our opponent hits the ball and to where. And we could keep looping this until we're done. So that's a simplified view. Of course, there are additional things that would need to be done. But if we wanted to develop this robot, we would typically break up each one of these tasks and design development stages accordingly. And in fact, the teams for those individual functions might well do the same process again and subdivide further. Our components might look something like an optical detection system, a purely computer-based logic system based on grade 11 physics trajectory, a movement system involving motors, a strategic system that produces the target to which we're going to try to put the ball, involving AI and potentially a learning system, a strike system with motors, levers, etc. And you get the idea. But we can put individual teams on each of these, and the good news is we can work concurrently, and the invention can be produced in this century instead of next century. But one key question is, how do you make a widget work without the rest of the device being ready? Well, this idea takes a bit of practice. And usually what we'll do is we'll hardwire hard code stand-in situations in place of the missing widget. So, for example, we want to eventually have a sensor that changes resistance based on a given situation, but it's not ready. It's on back order or it's in development. So we can temporarily wire in a variable resistor so that we can manually simulate each of the situations we need to. And then we can develop the thing we need to while we wait for that sensor. Or we want to communicate through a custom LCD screen that's being built by a different team. Well, we can substitute an LED for our output. So we can go and build everything we need to build, and it just lights an LED that stands in for the graphic that we're eventually going to produce. And many of you will have already noted that what this means is we're writing code and we're wiring things up that we're eventually going to take apart, that aren't going to be part of the final invention. And while that may seem like it's more work, this small bytes approach is actually in the long run much more efficient. So that throwaway code and those throwaway circuits may have to be discarded eventually, but the core thing that we're developing will transfer directly and slot into our overall project. And the time that we spend on this temporary wiring and coding, that time that doesn't go into our eventual device, will be much, much less than we would spend trying to troubleshoot a complete device with 7, 8, or 196 things wrong with it. Quick note, and this applies more to industrial engineering teams than our teams today. Our teams are small and our devices aren't that elaborate. However, big engineering projects can have multiple teams, and quite often these days on multiple continents, or even they can pay development firms outside of their company to develop individual pieces of the puzzle. And when this happens, as the projects get larger, documentation gets more and more and more important. For example, what if the team building the sensors doesn't communicate well with the team making the detection system? Well, in the end, the sensor gets delivered and the connection point doesn't work. It's not communicating with it, and one of the two widgets has to be completely redesigned. It's very important that the contact points between the mini projects be well documented, the inputs and outputs. And so these interdependent teams really have to do an excellent job of collaborating and documenting linkages. Okay, to summarize, even the simplest of our inventions need to be broken into development steps. This helps us with analyzing the overall project. Some people call it analysis paralysis, where we spend days trying to appreciate what a project needs to be. It helps with attributing responsibilities, breaking the project up to its individual teams. Parallel development streams are much faster. We don't wind up waiting for a given thing to be delivered before we can start on the next thing. And perhaps most important, troubleshooting is much, much more efficient. So the effective subdividing of projects does take practice, but it really is a critical part of the development process, and it's something that we should be certainly starting to learn in TEJ3M. Thank you for your time.